rotates. And as the rotating happens and flyable goes up and down, and we can do jumping of the valve. And the valve decides how much steam goes into the engine. So the big actually we have the limitation of the fly valve goes up and down. We have limitations. So that to say the speed, engine speed runs within the range. It will not over the most the maximum speed or the minimum speed within the range. That is how this works. So but sometimes we get disturbance input. Like motor speed now is lower than desired speed. So what happens? Centrifugal force of the rotating ball decreases. So the ball goes down. Then the steam supply becomes more, motor speed becomes fast. As long as the motor speed and it comes to desired speed. When the car engine speed automatic control system travels with the desired speed, the steam will not go into either side of the hydraulic. So if we divided the whole process into 3 steps, then we have the first step. Read a speed indicator to observe to speed. So we must know the motor speed and then first. Then have a desired speed ND. Unless we get the arrow, name it E equals ND minus N. If E bigger than 1, set the flow valve to increase the steam flow rate. The M is to increase the actual speed and N. Otherwise, E smaller than 0, set the flow valve to decrease the steam flow rate. The M is to decrease the speed. So actually, it seems the figure shows they are difficult, but the process is not that hard to understand, right? So first we should have actual speed, then desired speed, then get the arrow. And how to control depends on the actual figure than the So we take these two in comparison. Difference between automatic control and manual control before once. We see comparing and setting our performance by the controller automatically roll the forward, right? And an important conclusion is what? Automatic control process is includes measuring values of the control variables automatically, and then correcting errors automatically. As we get the desired speed and we have actual speed, then we get error. What we want to do is to minimize or to let the error be zero. Or maybe sometimes we can't set it to zero. Clear, close to zero, right? Yes. This is what automatic control does.
Okay, can you go? Okay. It's like who said this entity desired speed?
Yeah.
Who said it? Yeah.
Because the desired speed did not change, but speed is changing. According to the control. Speed equals to desired speed. So the E equals 0. So the control process. Okay. Yeah, because we made our requirements within our target.
If you know usual this zero, how to set this desired speed there?
Oh, to set the limitation of the flywheel, how up and down it goes. Just to set the limitation. So this range is the desired speed. You just get the desired speed, you cannot over the upper position or lower. So you have a range.
Yeah.
For that kind of for the car engine system, you cannot set just a number, exact number, exact speed, but it's a range. difference, how up it can go and how lower it can go. Not actual, the real number of the exact speed you want. So if we draw the picture of the schematic block diagram of the same value, this is the typical block diagram of a control system. So you should know the control object, of course. And then you will have a desired value. And the control objects will outputs and control outputs. Here, then we compare actual value with desired value, and then we get what? E is what? That's the difference, right?
Yes.
And the difference will transfer to maybe some instruments like amplifiers, actuator, maybe the motor sometimes. And then these instruments together change the output of the control object. Then the value will change. That's all the value here is equal to desired value. The E means 0. So we get our target actual value can be the desired. And this, look, we should have a sensor. Have you ever heard the word sensor? Yeah, this sensor to do the transform to measure the real outputs and to send it back to the desired value and make the together. This is how this. That's for the car engine system. We had a simple one, and for this we should have the one for this. And in this whole system, what plays the role of sensor? Rotating ball. See, the rotating ball plays the role of sensor. So here we picture a rotating ball, and then rotating ball is the feedback. And what is activate? Make change. What is activate? The engine. See, because we want to control the valve open and close and control the seat is to control which part seat. Wheels, of course, right? Because wheels is to adjust the seat whole car. So now the control object is wheels. So for actuator, steam engine plays the role of actuator. And who plays roles of amplification and actuator and control of steam flow rates. Yeah, this law, right? And what is the controller? Of course, is what? Wheels. And who plays the roles of comparison and amplification to make the difference from real value and target. Yeah, and the language, but it's true. And what is super red? To see what is the design, of course, desired speed. So after done this, we finish the block diagram of the whole car speed engine system. So is that hard? Not that. But for yourself to do it alone, maybe it's different. Maybe you cannot tell which plays the role of which, right? And this, you should remember by this figure, because it helps you to locate the parts from parts, which plays the role of the operator, sensor, always. You should first to tell which part. So now we see the structure or block diagram of the control system. And here are the main parts of And here we see a circle with cross sequence. We call it summing point. And its actual function is what? To get the difference, gets average. So it's a what? Compare what? Compare the function value with referencing, right? So this one works as comparison. The starting point here. It's the descriptive symbol used in block diagrams. The aggregate summation of two or more signals, not only two, maybe sometimes more than two. The direction of information flow is indicated by arrows. We have arrows here, indicates how the variable goes. And the aggregate nature of the summation by plus or minus class. And here we can see a plus here and minus here. So the arrow equals to what? Which minus which? R minus B.
B.
But if they're opposite, then things are right. So you should pay attention to the symbol here. A feedback or closed loop control system. It control system which tend to maintain a prescribed relationship of one system variable to another by comparing functions of these variables and use the difference as means of control. So we see why we call closed loop. Because from the structure we can see it has a what? Closed loop. Can you imagine if in the system can we have a node loop or one direction control? No. Then we will tell you some of the examples of the open loop system. The controls out the variables is that quantity or condition of control system, which is directly measured and controlled. So for the engine systems, of course, speed, right? And if for our body temperature is what? Temperature. And the reference input R here is a signal established as a standard of comparison for a feedback control system. A constant value of R is also named a set point. So that is say the desired value could be a constant value or could be a changing value, right? But if the desired value is a constant value, then we can say it is. But if a changing value, then the primary feedback signal B here is a function of the controlled variable C, which is compared with the reference input R to obtain the actual signal. The system value here is the value that ideal or desired value minus what? Minus the automatically controlled variable B. Because the symbol here shows R minus C. But sometimes the things are not ideal. We may have what disturbance, like the noise or kind of signals that the disturbance increases. So disturbance U is a signal other than not R, which tends to affect the value of the controlled variable. Disturbance is also affecting, but it's not the affecting we want. So we aim it to disturbance, and it's working up on the controlled object. So how do we know or learn how does this system work, good or not? So we may have some practice or index to measure the situation, the control situation. So here shows dynamic properties, session response indices subject to unit definition. So here, the blue line is the input signal. So what's the desired value? Just one, constant one. So it's a set point. So we can say for the instant the set point is one. And when we set the point to one to the desired value, and the whole system works. And the output value. And this term is the output value of the control object. And we can see under the 7.1, it has like a little bit shape before oscillation and then goes to stable. Okay. And here we can see the maximum difference here shows like a summit. Okay. We call this bigger than one part, bigger than one, call it overshoot. And here, this part named MPT is the peak value of the time response, the maximum value. And we can name it a percentage overshoot, PO. PO equals to the maximum minus the final value and divided by final value plus the percentage. This is an index to measure how much overshoot you can have. So you can get, do we want a big overshoot or small? Of course small, because sometimes the more bigger the overshoot is, the system is more unstable. Or maybe sometimes you can like the system cannot function well. So sometimes most of the time we want a small overshoot for the system design. And the settling time TX here. Time TX. The settling time TX also control system. It's the time to settle within a tolerance band of the final value without tolerance band. Because if we just want it goes to one, it will take a long time. So we name a tolerance band. If the curve goes into the tolerance band, we said, oh, it's okay, it's functioning good right now. Either side has a desired value. So we have a tolerance band. So the value, the output value can be a little bit bigger than when or a little bit lower. Both okay.
Okay, how to get this final one?
Oh, the final value. We can use an instrument to get this picture, to get this curve of the output of output value. So we'll draw the picture on that screen of that kind of environment that we can see the curve. When the curve goes stable, the stable value is what? Right. So you just need to wait to see. Maybe it's a very fast system, maybe just 2 seconds. So maybe it's a very, very like very slow system. Then like heating water. The much the water we have, the heating time needed more than maybe you need like 5 minutes to heating a water to 100. So the TS settling time is a very fast system. Depends on its flow. And the swiftness of response is measured by the rise time. TR, rise time. What is rise time? Just the TR here. Overshoot? No.
No. And the input.
The input or the final value, right? So the input is 1 and the final value is 1. So the first time to get to the 1 is the rise time. What is the peak time? Yes, the time is overshoot.
The overshoot. Higher you want to watch the main does it affect how long it takes for the desired value to achieve?
Yes. Yes. Said before, stability. it's a very important policy. It's the basis for system to function well. If the system is not stable, then you should control it. And let's see, the left-hand side figure shows a stable system. And right-hand side shows unstable system. Can you tell me the difference?
In an unstable system, we are moving from a more stable to higher and lower peaks. In the stable one, we are moving from higher and lower peaks to more stable or larger.
Yeah, but in more details, we can say, let's say here, the output of a control system is usually the function of what? Time, of course. And it changes with time. So in this figure, the difference between the control object value and reference for value decades to them. As long as the time goes, finally it will decades to zero. Like this is the red line is what input, and the black line is what output. As long as the time goes, output what come clearly
the same.
come closely to the input. That is to say, the reference value and the control value difference between these two decades to zero, right? And or the output coverage to a limit at the limit, then this is said to be stable. Otherwise, it is unstable. Since from the very beginning, it's stable. But as time goes, output gets very slow at no limitation. So this kind of situation we call this is unstable. A practical closed loop control system must be stable. Closed loop. So this we can say that is what we talked before. Stability is the first concern of control system design. Stable.
You mean this closed loop means?
Oh, we will tell. So next slide. And what is this? Time goes. We can guess the final difference between what the design value and the real value, right? So the left figure steady state arrow is equal to infinity, right? As it goes, it's well the difference goes larger. And the middle steady state arrow is equal to a constant, like K. R cover K. The right picture steady state arrow is equal to 0. Accuracy of those three systems. The right one is the better one, of course. Have you ever heard the word robustness? What is robustness? In control systems, robustness means the system ability to decrease the affection from disturbance. Sometimes a system, if the disturbance is very large, maybe you can get the system unstable or not very well functioning. That is to say, the robustness of that kind of system is not good. But sometimes, no longer disturbance is large, the system itself can function well still. So that is to say, that kind of system has good robustness. Let's see these two block diagrams. Figure A. The feedback system with some kind of disturbance here. See, NS means disturbance. We have the control loop, we have the desired value, output value still has disturbance here. And we can introduce a feed forward. We have disturbance here, but we have one more loop here. See the run. a big for control signal GC here. In order to what? Its target is to reduce the steady state error caused by disturbance. So that is to say, compare the two, which system has better robustness? Yeah, second, because it has some ways to reduce the fraction of this piece. But this one, no.
But this disturbance in the same system.
Yeah, of course, because
It's the same.
you should consider other conditions. The only difference here is here. Yeah. So we call the system of figure B has more robust than the system of figure B. Okay, then let's come to all those systems. You make it every day in our daily life. There are lots of systems, and most of them are closed, but some of them are open. Let's see. Toaster. You like toast? That's correct. It's pretty good to you. Those things for our okay, see the automatic toaster. Though it calls automatic, but sometimes we have no here or timer here to set the time for means the time, the long of the time is the darkness we want for the toast, right? We turn the knob. And the crispness of the toaster produces the output calling. What is the output calling? Positive. It's the darkness you get from the toast after the knob goes, right? And the crispness of bread is not satisfactory. This condition cannot automatically alter the length time. Since the output constant has no influence on the input constant, there is no feedback in this. See, we have no feedback.
Okay.
Once we set a node, after time goes, we get the bread. But if the bread darkness is not we desire, we want, but this button cannot automatically change the length to make the darkness meet your requirement. So we don't have feedback in this. So this is what? All the system. So a system can control in both ways. You should bet. Of course, to close loop has to that. So we can adjust by the feedback. Yeah, this is what we face every day. Elevator. So control system of elevator. How does it work? First, you should have this serial diagram. Law diagram. So think about this kind of situation. Tommy now has tennis ball, and he pressed the button at time of 10:15. And he wants to go higher to 20 seconds. And then at time goes the jack now at his floor, and he pressed the button. His desired floor is 20 seconds. So we consider the two time points. So we can draw the picture, or we can think about the broad diameter of both 2 points. So for this time, let's do it together. For this time, what is desired data reference input for this time? For this time, what is the desired data? Desired data. 20 seconds. Because at this time, Tommy he takes control. So this is that value, what he did, right? So it's 20 seconds right now. And then what is the key value? What is the value it's counting right now at this time point at 10 seconds? So the feedback of the desired value of the reference, the feedback is the input value. So what is the feedback be here? So that right? So it's what? So we get the arrow between these two is what? 12. We get this plus this, and then we get 12. And do we just turbulence right now at this time point?
Yeah.
No, right? Not disturbance. At this time, just Tommy press the button. No others, so no disturbance. So here should be what? 0. And then we skip to time points later. At this time, who will take control? The back. Now it's back to control. And so now what is desired? Still 2 seconds, right? But actual value here changed. No longer 2 is left. So right now, what is the 6 signal B? B, not F. But for X, it's right. And now think about this. Do we have disturbance at this time point?
Okay, 5, 10.
It's 5. Maybe this is what is the most confusing part. For this time point, is the disturbance time point.
Oh, okay.
Has the actual value in the control output and also the disturbance. Because it's not what we want. It's the medium variable, right? We want those 20 seconds. So this one is the medium variable. It becomes disturbance rate. It is the most confusing part of this whole problem. Okay, we have discussion here. This is the sentences you use every day. And can you name it open or closed loop? Which now see for that it's adaptive to control. So it should think things from the perspective of that. And now that is at what? 50th floor. But 50th floor is what is not he wants. He wants what? 20 seconds. So this is desired. But 50th floor is what? The medium, right? So we should think about their beginning. What is the floor from their beginning, the elevator begins? 10. So we have 10, 20 seconds, and 15. Yeah. So 10th floor is original floor, and desired is final floor. One goes up to 20 seconds. So the medium dividable 15th floor becomes 6 weeks. We treat it as 6 weeks. But not what from the very beginning. Yeah, because of so what we want and it's not original, so it becomes the medium. It's disturbance. So we can have this discussion about which of the following mechanisms belongs to closed loop. Maybe I rest and just discuss and we can talk about this later.
You know, work. And we guys like to every month. This John to see. No. Every month they're really.
Well, I mean, it's almost like money is a pop cupcake. But money. No, every time it's like, shall I say,
Oh, what about this, this five, is it serious? Huh? English is like. Oh, how much? If take someone having. I thought you were.
what?
Okay.
Oh, I should. I do. Right. I'm like. All right, that's enough. It's like that.
So you don't know how to play my. Every month,
So,
What happened to?
so,
100, I think, sure.
yeah. 3,000.
So what do you think about this?
Yeah, class are very.
Class.
I saw.
Yeah, only.
Maybe just.
No, I think.